For over a century, physics has been guided by two magnificent, yet profoundly different pillars of understanding. On one side, we have Albert Einstein's general theory of relativity, a majestic framework that describes the universe on the grandest of scales. It paints a picture of gravity not as a force, but as the gentle curving and warping of space-time itself, dictated by the presence of massive objects like stars and galaxies. It is a theory of the large, the smooth, and the predictable, governing the stately dance of planets and the inexorable expansion of the cosmos. It works beautifully when we look up at the heavens and contemplate the vast cosmic ballet. On the other side stands quantum mechanics, the equally successful but far more bizarre theory of the very small. This is the realm of subatomic particles, a world governed by probability, uncertainty, and strange quantum leaps. Unlike the deterministic universe of relativity, the quantum world is a place of constant flux, where particles can be in multiple places at once and energy comes in discrete packets, or quanta. It is the foundation upon which much of modern technology is built, from lasers to microchips, explaining the microscopic forces that hold our world together with astonishing precision. It is the language of the infinitesimally tiny. The trouble arises when these two great theories are forced to meet. Their mathematical languages and fundamental principles clash violently. When we try to describe situations where immense gravity is confined to a tiny space, such as the heart of a black hole, or the very first moment of the universe at the Big Bang, the equations of relativity and quantum mechanics break down, yielding nonsensical answers like infinite energies and probabilities. Physics has been searching for a single, overarching framework, a theory of everything, that can seamlessly weave these two descriptions of reality into one coherent and elegant tapestry. String theory is, by far, the most ambitious and promising candidate for this ultimate theory. This quest is not merely an academic exercise. It is a search for the deepest truths of our existence. We want to understand the fundamental rules that govern all phenomena, from the smallest flicker of a subatomic particle to the grand, sweeping evolution of the entire universe. A unified theory would represent the final chapter in a story of discovery that began with our earliest ancestors looking up at the night sky in wonder. It would provide a single set of principles from which all of physical reality could, in principle, be derived. String theory proposes a radical and beautiful solution to this long-standing puzzle, suggesting that the universe's ultimate secrets are written in a language of vibrating energy. The journey of string theory began in the late 1960s, not as a theory of everything, but as a more modest attempt to understand the strong nuclear force, which binds particles together inside an atom's nucleus. A young physicist named Gabriele Veneziano stumbled upon a century-old mathematical formula that, by pure chance, seemed to describe the interactions of these particles perfectly. However, the model had strange features and was soon superseded by a more conventional theory. For a time, this mathematical curiosity was largely set aside, seen as an interesting but ultimately failed idea. It was a dead-end street in the bustling city of particle physics. It was not until the 1970s that a handful of physicists, including John Schwartz and Michael Green, revisited the idea with a revolutionary new perspective. They realized the theory was not describing point-like particles at all. Its mathematics was describing the interactions of tiny, one-dimensional, vibrating loops of energy, strings. More importantly, they discovered that one of the theory's supposedly problematic particles behaved exactly like a graviton, the hypothetical quantum particle that should carry the force of gravity. This was a breathtaking revelation. The failed theory of the strong force was, in fact, a quantum theory of gravity. The central idea of string theory is astonishingly simple and elegant. It proposes that if we could zoom in on any fundamental particle, like an electron or a quark, we would not see a dimensionless point. Instead, we would find a minuscule vibrating filament of energy. Just as a violin string can vibrate at different frequencies to produce different musical notes, a low C, a high G, these fundamental strings vibrate in different patterns. Each distinct vibrational pattern corresponds to a different kind of particle. The universe, in this view, is a grand cosmic symphony, with all the matter and forces we see arising from the music of these elementary strings. This simple shift in perspective from zero-dimensional points to one-dimensional strings has profound consequences. It elegantly solves the problem of infinities that plagued earlier attempts to unify gravity and quantum mechanics. Because strings are not single points but are slightly spread out, their interactions are smoothed out, taming the violent quantum fluctuations at tiny distances that previously made the equations unworkable. The theory naturally includes gravity, not as an afterthought, but as an essential and unavoidable part of its structure. The same framework that describes an electron also describes the graviton, unifying matter and forces in a deeply satisfying way. As physicists explored the mathematical structure of string theory, they uncovered a startling and mind-bending requirement. For the theory to be mathematically consistent and free of paradoxes, the universe must contain more dimensions than the three of space, length, width, and height, and one of time that we experience in our everyday lives. Early versions of the theory required a staggering 26 dimensions, while the more refined and modern superstring theories, which incorporate a key symmetry called supersymmetry, operate in a universe with 10 space-time dimensions, 9 of space and 1 of time. This idea of extra dimensions might sound like pure science fiction, but it has a surprisingly plausible explanation within the theory. String theory suggests that these additional dimensions are not missing. They are simply hidden from our view. They are thought to be curled up, or compactified, into an incredibly tiny, complex shape, far too small for us to perceive or for our most powerful instruments to detect. Imagine a long, thin garden hose. From a great distance, it looks like a one-dimensional line, but for a tiny ant walking on its surface, it has a second dimension, the circular path around its circumference. The extra dimensions of string theory are like that second tiny dimension of the hose, curled up at every point in our familiar space. The specific geometry of these curled up dimensions is not just a minor detail, it is of paramount importance. The precise shape of these hidden dimensions determines the ways in which the fundamental strings can vibrate. It is the geometry of this multidimensional Calabi-Yau manifold, as it is known, that dictates the vibrational patterns and therefore dictates the properties of the particles we see in our universe. It determines the mass of the electron, the charge of the quark, and the strengths of the fundamental forces. In essence, the laws of physics that we observe are a reflection of the intricate shape of these unseen dimensions. This concept offers tantalizing, if speculative, answers to some of the biggest questions in cosmology. For instance, the mysterious dark matter and dark energy that appear to make up 95% of our universe might be phenomena whose origins lie in these extra dimensions, perhaps through gravitational effects that leak into our familiar dimensions. Similarly, string theory provides a framework for exploring what happens inside a black hole, suggesting that the singularity at its center might be replaced by a dense ball of strings. It offers a potential glimpse into a reality far richer and more complex than we can directly perceive, a hidden architecture shaping the cosmos. Despite its profound mathematical beauty and its potential to solve some of physics' deepest puzzles, string theory faces a significant challenge. It is incredibly difficult to test. The strings themselves are thought to be unimaginably small, far beyond the reach of any particle accelerator we could feasibly build. Proving their existence directly would require energies trillions of times greater than what the Large Hadron Collider can produce. This lack of direct, testable predictions has led to a deep division within the physics community, creating a rift between its passionate proponents and its steadfast skeptics. For its supporters, the allure of string theory lies in its sheer elegance and explanatory power. It is the only framework that seems capable of unifying general relativity and quantum mechanics in a consistent way. The fact that gravity emerges so naturally from its mathematics, rather than being forced into it, is seen as a powerful indicator that the theory is on the right track. Many physicists believe that such a beautiful and comprehensive mathematical structure is unlikely to be a mere accident of human imagination. They feel it must be connected to the true workings of the universe, even if we cannot yet see the full picture. However, critics point to the lack of experimental evidence as a fundamental flaw. Science, they argue, must be grounded in falsifiable predictions, ideas that can be proven wrong through experiment. String theory, in its current form, does not make a single unique prediction about our world that can be tested. Furthermore, the theory allows for a vast landscape of possible universes, perhaps 10 to the power of 500 of them, each corresponding to a different way of curling up the extra dimensions. This makes it difficult to explain why our universe has the specific properties it does, a problem that some see as a critical weakness. Ultimately, string theory remains a work in progress, a magnificent but incomplete edifice. It is a frontier of human thought, pushing the boundaries of what we know about space, time, and reality itself. Whether it will one day be crowned as the ultimate theory of everything, or be relegated to the history books as a beautiful mathematical dead end, remains to be seen. For now, it continues to inspire a generation of physicists to keep asking the biggest questions and to continue the centuries-old quest to read the universe's secret code. A mystery that continues to unfold with each new calculation and idea.